Hello, Analysis 1B. It is late night lesson time. So we're going to do the lesson. This is the lesson that you guys will be watching for November 10th or 11th. November. That does not look right. November, but that's right, I guess. November 10th or 11th. This is Analysis 1B. Analysis 1B. Remember that as you're watching this, the week coming up, which starts on Monday, November 9th, there is no school on November 9th. So November 11th, which is a Wednesday, is replacing that day. So if you have this class first, second, third, or fourth period, or I suppose whatever you do have first, second, third, and fourth period, you will have those classes on Wednesday, November 11th. Wednesday, November 11th. So what are we doing today? Students will be able to... we're reviewing sequences first. Review sequences. We're going to talk about a few new theorems about them. We're going to be specific with some formalism relating to limits. Formalism connected to limits, right? Because now we've done limits formally in Analysis 1A, so we can use limits as we're talking about sequences now, whereas when you did sequences in pre-calc, you were a little sketchy on them. 3, we have a couple short theorems about how to manipulate sequences. And 4, we have sort of an overview of methods. Overview of techniques. So we will talk about a number of techniques with sequences. I keep doing that, I'm sorry. This is section 9.1. I like to think of 8.7, which is L'Hopital's rule, 8.8, which is improper integration, and 9.1 is kind of forming a mini unit. So this is a little mini unit about dealing with infinity, right? L'Hopital's rule, dealing with infinitus, of course. Improper integration, dealing with integrals that are allowed to go out to infinity. And now sequences, talking about sets that go to infinity, right? And evaluating what's going on with sets that do so. And then in 9.2 through the end of chapter 9, that's when we're talking about series instead. So it's a very... a topic based on what we're about to talk about with sequences, but significantly different. There's a key major difference as we move into the rest of chapter 9. So think of this going along with L'Hopital and improper integration. You have done sequences already. So what is a sequence? Let's do some initial definitions, right? Let's make sure things make sense. So what is a sequence? Cat is going crazy. What are you doing, cat? I don't know if you can hear her making noise running around the room. But a sequence is an enumerated list. Enumerated list. It's a list with an order, right? It's an ordered list, and specifically one that you have identified numbers for each piece of the list. The terms of a sequence are the elements of the list, right? Term 1, term 2, whatever it is. The enumerated list, by the way, is generally enumerated by the natural numbers. You don't have to be, but that's usually what you do. We can talk about the nth term, for which I'm not going to write an explicit definition. This is the term that comes in position n. Right? Whatever n may be, it can be the first term, the second term, the third term, the 19th term, the 22nd term, the kth term, or the nth term for that matter. And then we have recursive versus explicit. So recall a recursive sequence, for example, could be that I tell you that the first term is 1, and I tell you that after that, term a sub n plus 1 is term a sub n, and I add 2 to it. So when in this equation n equals 1, then I'm saying that a sub 2 equals 1 plus 2, which is 3. I'm saying that a sub 3 is equal to a sub 2 plus 2 more. That would be 5. So if you think about this for a sec, this is the odds defined recursively. The previous thing plus 2 more. That's my new term. So we could also do that explicitly. We could say that a sub n is equal to 2 times n minus 1 for n greater than or equal to 1. Right? Starting at sub 1, I have that a sub 1 is 2 minus 1. I have that a sub 2 is 4 minus 1, 3. A sub 3 is 6 minus 1, 5. So we can have series that are done recursively or explicitly. Now there are some series that you can only write in a recursive form. You can't evaluate for an explicit function for them. You can force that to happen. Explicit can, I want to say, always be done as recursive, but I could be wrong about that. I'm trying to think of a counterexample. Maybe I would do something weird with trig and force it to not be able to be written as recursive. I think that's possible. So some definitions. Again, you know these things. These are things you've done before. This is review. Formalism. Right? Formalism. What are we really saying here? Definition. Limit of a sequence. And you might be thinking, we already know how to do limits. We have a definition of limits. Why do we need to talk about this? Consider the following. Let L be some real number. We say that the limit as n goes to infinity of a sub n is equal to L if and only if there exists an epsilon greater than 0 such that for all capital N greater than 0, there exists an epsilon greater than 0 and there is a capital N greater than 0 such that for all little n bigger than capital N, that will imply that the difference between a sub n and L is less than epsilon. You thought you were free, but no. We will pull you back. Why are we doing this, though? We've already defined limits. Why are we bothering? Here is the key. This is not a function, or better, I should say, not a continuous function. Limits are discrete. There exists an A1, there exists an A2, there exists an A3, there exists an A4, but there does not exist an A sub 3.7, or an A sub 3.9, or an A sub 3.94. It's discrete. And our understanding of limits thus far has been specific to a continuous variable. The function itself might have discontinuities, but in the interval we look, in the region around epsilon, in the region around delta, really. There is no delta in this version. We are guaranteed existence, right? We're guaranteed continuity on an interval. Here, we're not guaranteed continuity on an interval. In fact, we don't have that. We have a discrete list instead of a continuous variable. And for that reason, we need to discuss limits anew. We need to consider what it means to have a limit with a discrete variable. And you've noticed, I hope, the one key difference. Instead of using a delta and saying that the input variable A, the input variable, which would usually be x, has to be close to the center, or in the case of infinity, far away from 0, is how we define those, way back in 2.5 and 4.5. We use the discrete n. It's not explicitly said to be discrete, but that's our intent here. And we say that for every element of the series beyond that spot. So starting at some point, all the parts beyond it. So what's this really doing? Well, this is equivalent to our definition before. It really is. If instead of thinking a sub n, you think f of n, this agrees with our old definition. We didn't really do anything new here. It really is the same idea. But the key difference in concept is the definition we had before was for a continuous variable. We need to know what we're talking about for a discrete variable. Turns out we're talking about the same thing. It's okay. And we get, therefore, convergence and divergence in the same way as before. When such an L exists, when this definition is satisfied, we say, yep, sounds good. That limit converges. And when there is no such limit, we say that that sequence diverges, right? So a sequence can converge to L, which is to say the limit converges to L, or a sequence can diverge, that there is no limit. As before, if the limit is infinite, that is a special case of divergence, right? A series can diverge to infinity, or it can diverge in that there is no understanding of the limit at all. There is no meaning to the limit at all. Both of those are forms of divergence. What was the point of this page? Our definition thus far was for a continuous variable. We need to say what we mean for this discrete setup. Turns out we mean the same thing. And we get a couple short theorems. How do we actually deal with limits of sequences? For some real number L and a function f mapping from real numbers to real numbers, such that the limit as x goes to infinity of f of x is L, if for all natural numbers n, f of n is equal to a sub n for sequence a1, a2, etc., then the limit as n approaches infinity of a sub n is L. If I have a function that has a limit, and here's the key here, when I plug natural numbers into the function, I get my sequence. When I plug in anything else, who knows what happens? I don't care. I don't care what f of pi is. I don't care what f of 9.4 is. But when I plug in 10, I better get a sub 10. When I plug in 11, I better get a sub 11. When I plug in 93, I better get a sub 93. When I plug in 93.1, I don't care, right? But they have to agree. The sequence and the function have to agree when I plug in the natural numbers. Then I get that the limit of the sequence is the same as the limit of the function. And in general, this is how we solve for limits of sequences. We convert to a continuous variable and use all of the techniques you already know. If you can prove that limit exists, we're good to go. What about the converse? If I have a limit of a sequence, does that mean that any function which agrees with it on the naturals would also have a limit? Notice, by the way, we only care about limits going to infinity. Every time I say limit, I mean a limit as the variable goes to infinity. What about the converse? Consider the following. What if my f of x function is 1 when x is a natural number and 0 otherwise? I want you to think about the sequence we would compare this to, the value of f for each natural number, and whether that has a limit. And then think about whether f of x as a continuous function, sorry, not a continuous function, f of x as a function of a continuous variable x. If x can be all real numbers, does that have a limit? And I intentionally won't answer this. I'm going to make you answer it. But again, think about if we make a sequence which agrees with f of x for all the naturals, does that have a limit? compared to f of x itself having a limit or not, as x goes to infinity, or as the natural n goes to infinity, right? And that's what I want you to think about for the converse of this theorem, to determine whether or not it's true, to convince yourself at least whether or not it's true. So there's theorem 1. Theorem 2. Notice we didn't prove theorem 1. Sorry. We're not going to prove theorem 2 either. Theorem 2. Assume the following. That the limit as n goes to infinity of the an sequence is L, and that the limit as n goes to infinity of the bn sequence is K. I claim the following hold. That the limit as n goes to infinity of an plus bn is indeed L plus K. 2. That the limit as n goes to infinity of some c times an is indeed c times L for any real number c. 3. That the limit as n goes to infinity of an times bn is indeed L times K. And 4. That for bn not being 0 and k also not being 0, the limit as n goes to infinity of the ans divided by the bn's is equal to L over k. Sums, scalar multiples, which is to say multiplication, and quotients, products and quotients. All of these rules still hold. And why? Consider a function which agrees. All these rules work for functions. Now that said, as I hope you've realized, the converse of the previous theorem was not true. So just because a limit of a sequence exists does not mean that every function which agrees with it also has a limit. So you do have to be a little careful if you're thinking about these as if they were continuous functions. But this should feel plausible, right? We've defined limits to mean basically the same thing as when we were using the continuous variable x, where x can be any real number. So it stands to reason these properties should still hold. Theorem 3. Theorem 3. If the limit as n approaches infinity of an is equal to L, which is also equal to the limit as n approaches infinity of the bn sequence, and there exists some capital N, a natural number, such that for all the little n's beyond that number, an is less than or equal to cn is less than or equal to bn. Then the limit as n goes to infinity of the cn's is also L. There's a good name of this one. You know it. This is a theorem you already know. We're just doing it for discrete sequences now instead of a continuous variable x. This is, of course, the squeeze theorem. And it still holds just fine. No problem. I'll do an example of this one. And then we have one last theorem. I'll do an example of this one real quick. This is the classic example. This example is in your book, so I feel a little bad just using an example that you could read yourself. But this is the classic example to do. Note the following. Note the following. N factorial is 1 times 2 times 3 times 4, etc. up to n. 2 to the n is 2 times 2 times 2 times 2 times 2 n times. So I'd like you to compare, ignore the 1 for the moment, those two, and those two, and those two, and these two. With the exception of the very first term, every other term, the factorial piece is at least as large. And therefore I claim that for all n, that's at least 4. This 4 accounts for the extra 2, and the 3 is bigger than its partner. So as long as n's bigger than 4, n factorial is bigger than 2 to the n. Right? By the time I get to 4, it's now true. 1 is not bigger than 2. 1 times 2 is not bigger than 2 times 2. 1 times 2 times 3 is not bigger than 2 times 2 times 2. But the 4 accounts for its own partner and the original 2. And then the 2's match and the 3 is bigger, right? So n factorial clearly works here. I mean, and you could have just multiplied that, right? Like, you know that 24 is bigger than 16. But the point is the method. Because from now on forever, the new factor of the factorial is larger than the new factor of the 2 to the n, right? Why do I care? Because if I reciprocate, the order, the direction of the inequality changes. And furthermore, notice I could also include a greater than 0, right? 1 over n factorial is definitely at least 0 because n factorial is positive. Why do we care? Why do we care? Because we can't turn 1 over n factorial into a continuous variable. I can't use a continuous variable x and talk about the function f of x is 1 over x factorial when x is allowed to be a fraction or irrational. Fun fact, you actually can. It's related to something called the gamma function, but that's not for now. That's another thing entirely. Okay? In our experience, factorials need to work with natural numbers, right? Not negative integers and not irrationals. So I can't use the trick of checking a continuous variable, checking the x version of this factorial sequence, 1 over x factorial, and find its limit and then compare it, right? I can't do that. I can do it with 1 over 2 to the n, though. We know that we could say let the an sequence be 0, 0, 0 forever, right? A1 is 0, A2 is 0, A3 is 0. Let the bn sequence be 1 over 2 to the n. Which is to say, starting at 1, a half, then a fourth, then an eighth, then a 16th. And I claim that we know, certainly, the limit as n goes to infinity of 0 is 0. We know that the limit as n goes to infinity of 1 over 2 to the x, x goes to infinity, is 0, and therefore the limit as n goes to infinity of 1 over 2 to the n is 0. So we can also say let f of x equal 1 over 2 to the x, right? I converted my discrete b sequence into a continuous x variable, f of x, that we use. The f doesn't have to be continuous. It is in this case, but doesn't have to be, right? The x is what is a continuous variable, right? X is allowed to be all real numbers. So what do we have? The an sequence is always less than or equal to our function. The bn sequence is always greater than or equal to our function, and the limits on the outside are the same. So therefore, the limit as n goes to infinity of 1 over n factorial is also 0. Now, that shouldn't be surprising, right? Like, duh. N factorial gets bigger and bigger and bigger. So as it gets bigger, I'm dividing 1 by something growing unboundedly. Of course we get 0. Of course we do. But we had to prove it. And we couldn't prove it by talking about the continuous variable x, talking about 1 over x factorial. We had to use some other method. So there is our example of the squeeze theorem. Last proof in this list of proofs. Last proof in this list of proofs. Sorry, theorems. Last theorem in this list of theorems. It's probably shouldn't be recording this late, to be honest, right? But I want to get it done so I can upload overnight so I can make the quiz and then get it out to you guys right away tomorrow. Theorem. If the limit as n approaches infinity of the absolute values of the an sequence goes to 0, then the limit as n goes to infinity of the an sequence itself goes to 0. So if the ans mix positives and negatives, maybe they're alternating, positive, negative, positive, negative. Maybe they're not even alternating. Maybe they just do something bizarre. Some positives, some negatives, all mixed together. If we make them all positive, and that limit still exists as 0, if that limit is 0, then the original sequence has a limit of 0 also. This is a super useful technique for later in this chapter, for the unit to come about series. But for now, we're talking sequences. And this shouldn't feel like it's super useful yet. That's okay. I'm telling you, it's going to be. Proof. This one we're going to prove. Notice that negative absolute value of an is always less than or equal to an, which is always less than or equal to the absolute value. If the an is negative, it's equal to this part on the left, and it's definitely less than the part on the right. If the an is positive, it's equal to the part on the right, and it's definitely more than this negative thing on the left. And if the an is 0, then these are all 0, and we're okay. Right? An is definitely less than or equal to its absolute value, and more than or equal to the negative of its absolute value. So we apply squeeze theorem. If each of these limits exist, and they are 0, then the middle limit is also 0 by the squeeze theorem, right? That's the whole proof. That's it. Technically, we also used a scalar multiple, right? We factored the 1 out. The negative one, I should say. But this was just use the squeeze theorem, right? Bound an between its absolute value and the negative of its absolute value. Okay. And now we get into the parts that you might know, but they're not as direct, right? They might start feeling less intuitive, and that's okay. 2 new definitions. Definition number 1 is monotonic. Monotonic. And the definition of monotonic is non-increasing or non-decreasing. Non-increasing or non-decreasing. Notice this is not the same thing as decreasing or increasing. Decreasing and non-increasing don't quite mean the same thing. For example, 1, 5, 12, 12, 12, 19, 20, 20, 34. This is a non-decreasing sequence, but it is not an increasing sequence, right? Non-decreasing, yes. Increasing, no. This is, therefore, monotonic. Strictly monotonic means increasing or decreasing, for the record, but we don't really care about that. Monotonic, monotonic. Definition number 2. There are technically 3 different parts here, but we're going to define the idea of boundedness. We're going to define bounded. You can be bounded above, which means that there exists some real number m such that for every n bigger than, that's fine. For every natural number n, your ANs are less than or equal to that m. There exists some number which is bigger than all of the terms of your sequence, or equal. we can be bounded below. There exists a lowercase m, some real number, such that for all of the naturals, your sequence terms a sub n are at least as big as little m. So bounded below means there is something that is below all of your terms. And bounded above means there's something above all of your terms. And you can simply be bounded, full stop. So you can be bounded above, you can be bounded below, you can be just bounded. We don't say above or below, and that's both. So bounded above, bounded below, or just bounded, in which case both need to be true at once. The definitions of monotonic and bounded. The definitions of monotonic and bounded. I know this is kind of dry. I know, bear with me. The rest of chapter 9 gets way better, culminating in the single coolest math thing that you have done in any class ever. That's the end of chapter 9, but we've got to get there. We've got to build up the tools first. We're getting there, though. One last thing, and then a big important theorem. One last thing, then a big important theorem. The completeness of the reals, as in the real numbers, says, I shouldn't say says, implies, leads to the least upper bound property. The least upper bound property. And what that property says is, if there exists an upper bound, then there exists a least upper bound. For example, graphically, for example, if I have a function that does this, let's not use a function, let's use a sequence. I have a sequence that does this. So you can see that I have an asymptote there, right? I've drawn an asymptote. And the sequence continues. Those aren't dots of the sequence. The sequence continues, right? So this is a graphic representation of a sequence. A sub 1, A sub 2, A sub 3, A sub 4. This is a 1, that's a 2, that's a 3. I claim the following. 204 is an upper bound. 204 is an upper bound of this sequence. For every element of the sequence, for every term of the sequence, that term is less than 204. We're good. But much more to the point, 3 is also an upper bound. And it's a much better upper bound, right? In that it gives us a lot more information. It's a lot more useful to us. The way I've drawn this implies that 3 is the least upper bound, that the sequence gets as close to 3 as you want. It looks like it the way I've drawn it, right? That's what's intended here. This theorem, the least upper bound property, is true for real numbers. It's the actual theorem behind the scenes here. Is way beyond this course. It's also way beyond analysis too, for that matter. This is a big deal in analysis and the broader field of analysis, also a number theory sort of idea. This is way beyond what we're doing, all right? We're going to take this for granted. And we're only going to need it for one thing, which is what we're about to do, all right? We're only going to do it for one thing. which is the following, and also is our final theorem. Theorem. Monotonic plus bounded implies convergent. If we have a sequence which is monotonic and bounded, it's convergent. And what was monotonic again? Non-increasing or non-decreasing, which you can interpret based on the derivative, right? A positive derivative means increasing, a zero derivative means constant, and a negative derivative means decreasing. So you can check monotonic by turning a sequence into a continuous variable function, into an x function, and then checking about its derivative. Bounded is a little harder to check directly for us, but there are opportunities for us to do so, right? Primarily involving sines and cosines, or a function that's always increasing, we know would be bounded below, right? If it's always going up, then wherever you start is the lowest thing it ever is. For example, bounded and monotonic imply convergent. I'm going to prove this one. Bounded, among other things, without loss of generality, assume non-decreasing. We're going to assume this function's going up, not down. And then we're going to use that we are bounded above. If we wanted the non-decreasing version, we would use bounded below. Okay? Bounded means both, remember. So what's this tell us? Whatever A1 is, A2 is greater or larger. And A3 is bigger still or equal. And so on until, say, A sub n, however far you want to go. And for that matter, keep going after that. These are all less than or equal to some m. Definition of bounded. So here's the monotonic part. Here's the bounded part. Every single term is less than or equal to n. Therefore, there exists a least upper bound. Call that upper bound L. So now I have a least upper bound. I'm going to call it L. This is just saying there's some bound. I don't know. Maybe that's way too big. But there is a least upper bound, call it L. So what do we know? What do we know? For any epsilon greater than 0, epsilon minus L is less than L. So epsilon minus L is not an upper bound. What's it mean to be not an upper bound? Well, an upper bound means you're always bigger than every term. So to not be an upper bound, therefore, there exists some number, I don't know what, there exists some capital N in the naturals such that A sub capital N is bigger than L minus epsilon, right? If something is not an upper bound, I must at some point be bigger than that number, bigger than L minus epsilon. I don't know what it is. Maybe it's A sub 5. Maybe it's A sub 4002. Whatever, though, eventually I have some term that's bigger than L minus anything, no matter what that anything is. By monotonic, for every little n bigger than or equal to that capital N, we know that A sub capital N is less than or equal to A sub little n. So what else can we say? We know that L minus epsilon is less than A sub capital N, which is less than or equal to A sub little n. which is less than or equal to L, because L is an upper bound. So every term, no matter what, is less than L. And L itself is less than L plus a little bit. So for all little n at least as big as capital N, L minus epsilon is less than or equal to A sub little n is less than or equal to L plus epsilon. We've got it. For all little n at least as big as capital N, A sub n minus L is less than epsilon, right? This inequality statement is the same thing as this compound inequality. And that was the definition of a limit, the epsilon delta definition. No matter how small epsilon is, I know that there is some capital N, so that for every term beyond it, I am close to L, right? The output A sub n is close to L. Bounded and monotonic imply convergent. Why is this important? Because we don't have a lot of tools right now. Let's talk about the tools that we do have. Let's talk about the tools that we do have. Tools. Tool number one is epsilon delta. We can prove convergence or divergence of sequences directly. That is an option. We don't want to do it unless we need to. But it is an option. Two. We can use the absolute value implies original theorem. That if the absolute values make a series that converges, then the original thing also converges. Tool 3. Tool 3. Convert to f of x and do the limit somehow. Turn your sequence into a function of a continuous variable x and then do the limit. If that exists, your original limit was the same thing. Tool 4. Do algebra. Sometimes algebra is useful. This is most often useful when your terms themselves have multiple pieces. When your A sub n is some stuff plus some other stuff based on n. It's usually when algebra is the most useful. 5, squeeze theorem. It's an option. It's an option. And as always, of course, we have by smarts, right? Like, it's possible there's some weird, crazy situation. You just have to kind of stare at it until it makes sense. Not often, but sometimes. And finally, the combination rules. So for example, having two series that are added together and doing them each separately, right? But that really just takes you back to the top and you have to do it for two problems. So if you can do a combo rule, you just have to solve each of them separately and then put them back together again. So it's really doing everything else twice. I won't give you examples for everything, but I'll give you some. Okay. For epsilon delta, one good example of when to use epsilon delta is for that a sub n is 1 over 2 to the n. We did it by converting to a continuous function and saying, oh yeah, that's something we know. But epsilon delta works very well with 1 over 2 to the n. An example of the absolute value thing is when you have something like, say, negative 1 to the n plus 1 divided by 2 to the n. This thing bounces back and forth between positive and negative, right? I don't know how to make a continuous function about that. I also don't really have a good sense of epsilon delta for it. I could figure that out. But the absolute value of this, I don't care what's happening in the numerator, the whole thing just gives you a 1 in the numerator. So it's the same thing as 1 over 2 to the n when I do an absolute value. And that, we just said, you can do with epsilon delta. Convert to f of x into a limit. This is most useful for cases like, say, n cubed divided by e to the n. Because your instinct, I hope, doing a limit as n goes to infinity is to want to use L'Hopital's rule, right? The numerator is a polynomial. It'll eventually go away. The denominator stays put no matter how many times you apply L'Hopital's rule. But you can't use L'Hopital's rule on a sequence. Why not? Sequences are discrete. We cannot do a derivative of a discrete object. That doesn't make sense. But if we convert this and talk about x cubed over e to the x, a function based on a continuous variable that agrees everywhere except, agrees at all the natural numbers, then we're good, right? Then we could use L'Hopital's rule on the f of x function. Algebra, a good example is problem 62 in your book, which is n squared over 2n plus 1 minus n squared over 2n minus 1. That entire thing is the a sub n term. And if you do some algebra first, things work out nicely. Squeeze theorem. Stuff like, for example, sine of n divided by the square root of n. Right? Stuff with trig. I guess I will give you an example of everything, but that's okay. Stuff with trig. Example of number 6. Famous example. 1/2 times, you'll see why, 1 plus -1 to the n. So notice this one alternates. So sometimes it's 1, sometimes it's -1, which means this either gives you 2 or 0. Can't make a continuous function out of this. There's no algebra to do. I don't want to use epsilon delta on something like that. I want to think first. And see what happens. And then for combo rules, stuff like, for example, what would be a good example? 5 minus 1 over 2 to the n. I'd like to do this by talking about just 5 and talking about just 1 over 2 to the n, and then subtract those two separate limits, right? Something like that would be used. So I did give you examples of each. So these are examples. And I would encourage you, if you don't really feel confident about this yet, try one, or more than one for that matter, right? Those are examples. These are the techniques that we're going to be using for problems in class. And these are examples of when you might want to use them, right? The sorts of things to look for. And with that, let's go through the slides from today and call it a night. So what did we do? We reviewed sequences. You've already studied sequences. We reviewed some terminology. We formally defined a limit of a discrete sequence. We hadn't defined it yet. Turned out to be the same thing anyway. We did a bunch of short theorems. A couple we proved, many we didn't. And we did an overview of the techniques that we've talked about. We defined sequences and terms and nth term and recursive versus explicit, right? These are things you've done before. If you're rusty, I understand. That's okay. So does Kirk. But brush the rust off because you've done it before. We got to make sure it's okay. Talk to me, talk to Kirk. But get that rust brushed off because we're going to keep moving once we start on sequences and series. Definition, turned out it was the same anyway, right? We just had to be okay with that. We had to explicitly discuss it. Theorem number 1. If a function of a continuous variable agrees with the discrete sequence when you plug in natural numbers, the limit of the sequence is the same as the limit of the continuous variable function. And the converse I left for you to think about with this example. Theorem 2. All the combo rules still work. Sums and scalar multiples and products and quotients. Theorem 3. Squeeze theorem still works. And we did an example. The example, right? This is the example everyone does, but it's because there really isn't any other good way to solve this. It's an approachable question. What about the limit of 1 over n factorial, right? It feels like it should be 0, but we can't prove it directly. We have to use the squeeze theorem. Next theorem. If the absolute value of each term has a limit going to 0, then the original sequence with positives and negatives, whatever they are, also goes to 0. How? Prove it with the squeeze theorem. Definition of monotonic and of bounded. Bounded above, bounded below, and just the word bounded. Something way beyond this course. Way beyond this course. But why do we need it? I needed to say that L minus epsilon is not an upper bound in this proof. The proof that monotonic and bounded sequences are themselves convergent. If you are monotonic and bounded, you are a convergent sequence. And I needed the L plus epsilon to be less than my a sub little n. I needed L minus epsilon to not be a bound. If L is the least upper bound, then subtracting anything, no matter how small, is no longer a bound. This proof has some tricky bits to it. You should stop and think it through. And our tools. We can use epsilon delta. We usually don't want to, but it's an option. We have the absolute value implies something about the original sequence. We have converting to a continuous variable x. That allows us to use all of the techniques we know for f of x functions that we can't use with discrete functions, maybe. Sometimes you do algebra first, arithmetic, and just see what happens. The squeeze theorem is often useful with sinusoids, as usual. By smarts is stop and think about it and think what's really happening here. And the combo rules, right? You can break up into 2 separate pieces and do each separately and bring them back together again. So thus concludes our lesson. That's 9.1. Have a good day.